So today we're going to speak about genetic technologies in finding novel drugs. In no regards to genome editing, we're going to discuss molecular methods in novel drug identification, and that's the application of genetic technologies in molecular pharmacology and target therapy development. So what is target therapy? That's a pointed impact on fundamental molecular mechanisms underlying the disease development. So we are not targeting the whole organism. We're trying to directly eliminate the cause of the disease, and that's mainly regarding cancer cells generally. To be able to find a target therapy for a disease, we need to understand the molecular etiology and pathogenesis that is crucial for development of the drugs. Uh, Target therapy, as I've said, is suitable for neoplasia, both benign and malignant. And that includes also pharmacomatosis. Sometimes target therapy can be applied to neurodegenerative diseases and to some sort of metabolic dysfunctions. Examples of such diseases and such drugs include erlotinib, market name is Tarceva, and that was used for lung cancer, for example. Rituximab, the market name is Mabthera, that is anti-CD20 uh, genetic and genetically engineered antibody that is used for lymphoma or some leukemias. And for example, for myodystrophy, we can use Etiology, Translarma. That's also target therapy. So, when speaking about novel drug substance search, uh, we can choose several ways. We can either create a drug substance de novo that can be reached by random synthesis, by modification of a known drug substance, or by docking that was formerly named in silico modeling. Um, for this approach for creating drug substance de novo, we need a huge program of preclinical evaluations, and that includes uh, pharmacokinetics, pharmacodynamics, safety, mainly safety and toxicology studies, which include long-term mutagenesis and teratogenesis studies. Um, and also we need understanding of absorption, metabolism, and elimination studies. Overall process takes about 20 years and can cost up to $20 million to be completed. So here is an example of just a small excerpt from a investigator brochure that is submitted before marketing registration is received. You can see how many pages such a brochure includes. That's just, again, a little excerpt from the whole brochure. But luckily, there is a second approach that includes repositioning of the known drug substances. We have some certainly characterized drugs that have passed all the non-clinical evaluations, including safety. That is most important for us. And we can save a lot of time and money for such a drug substance, and just to see if it works for some other nosological forms, other diseases, um, and can be indicated for those diseases. So what do we do to find such drugs? It's usually pharmacological screenings using the disease models. And here is where genetics actually comes into scene. So pharmacological screening can be high throughput, that includes a lot of drugs to be tested, or a lot of proteins, or whatever we are testing, or low throughput. And one can also speak about medium throughput screenings. It can also be divided on the targets. So it can be molecular, using recombinant proteins that are involved in the disease pathogenesis or etiology. This can be cellular, in a living model, in a cell that was modified to model the disease, or a very rare form of the screening can be done on transgenic animal model. But that is extremely expensive and is only done in very rare circumstances. So today I'm going to give an example of such a pharmacological screening that will be based on my own research on neurofibromatosis type 2. And neurofibromatosis type 2 is an orphan disease that occurs only in 1 in 2,000 births. That's a genetic disease. And the clinical features include vestibular schwannomas, meningiomas, ependymomas, malignant mesotheliomas, and also lens abnormalities, predisposition to cancers, and some skeletal abnormalities as well. Why this disease? Because there is still no pharmacotherapy developed. Because the pathogenesis of the disease is very complicated. So nowadays, the main way to treat neurofibromatosis patients is surgeries, multiple surgeries, and this, of course, applies to neurosurgery or radiotherapy, and such an approach eventually leads to disabilities. Such patients lose balance, lose hearing, and unfortunately, they die before 30. Very seldom patients survive until 50. So what do we need to try to find therapy for neurofibromatosis or for any disease? We need to create a disease model for non-clinical studies. And this model should include several levels. So as I've said before, it can be a recombinant protein. This cannot be done for neurofibromatosis, and I'm going to discuss later why it cannot be done. We can also create a cell model for in vitro studies, and we can also do transgenic animals. That's not for screening. Mainly that's for mechanism clarification and efficiency testing. So the other thing we need to create a model, after we choose which level we use first, we need to create a model, and what we do need to create a model is to understand etiopathology. And of course, different levels of the models can be used for different study stages. So what is the etiology of neurofibromatosis type 2? This disease occurs due to inactivating mutations in an NF2 tumor suppressor gene. So it's a monogenic single gene disease. It is inherited by autosomal dominant way, and NF2 is a classical 2-hit inactivation tumor suppressor. Normally, healthy people are NF2 homozygously positive. NF2 negative homozygotes die early in embryonic development. And NF2 patients are heterozygous. So most tissues are heterozygous on NF2 gene. And when a spontaneous inactivation of the second allele occurs in neural tissues, this causes a development of the tumor. So this one is a homozygous NF2 negative tissue, and all the rest are NF2 heterozygous. So why is neurofibromatosis developed? Why is neurofibromatosis type 2 causing only neural tumors? Because in an adult or in a postnatal baby, NF2 gene is only expressed in neural tissues or some ocular tissues, and at quite a low level, it is expressed in connective tissue. Should it be the overall expressed gene, the consequences would be much harder. But still, it's quite a nasty disease. So what is the NF2 gene product, Merlin? That's a protein that was first discovered as a member of esverine-redoxynosin family, and it was deemed to be an actin cytoskeleton organizer. It still is deemed to be an cytoskeleton organizer, but now we know that Merlin is a tumor suppressor, and it suppresses a lot of signaling cascades. This mainly regards tyrosine kinases and subsequent cascades such as MEK-ERK cascade, PI3K-mTOR cascade. Merlin is also an inhibitor of P21 activated kinases of small GTPases such as RAC, MIST kinase, and eventually the YAP inhibitor, and also an ubiquitin ligase Cyrilline. That's only the known interactions of Merlin, and we suppose that there are much more. So that's about pathogenesis of NF2. So when Merlin disappears, we get the activation of all the mentioned cascades, and this leads to, some Russian here. This leads to migration and motility increase, and also expression of proliferative cascades. As you can see, the pathogenesis is extremely complicated, and you cannot just knock out one of the signaling cascades and get the disease cured. So there are different approaches to control the NF2-associated tumors. We can either inhibit the growth factors receptors with erlotinib or nilotinib, or we can also inhibit RAF together with tyrosine kinase receptors. That's done by sorafenib. We can also try to inhibit P21 kinases that would inhibit the MEK-ERK cascade. Or we can try the proteasome inhibitors that are the effectors of ubiquitin ligase Cyrilline. Another to use bevacizumab, that is VEGF inhibitor. And that is so far the only efficient way to treat neurofibromatosis, not to treat, but at least to control tumors. All the other ways cause the compensatory activation of other signaling cascades other than the inhibited one. So, what can we do to try to fix the situation? We can do a pharmacological screening to see if we have at our disposal some drugs that would affect the NF2 associated cells. And we need to obtain such NF2 associated cells, make a cell-based model. Because as you can see, the disease is caused by the absence of the protein. So we cannot use the protein model of the disease. but we can do an NF2 deficient cells. So to create a cell-based model, we can do the inactivating mutations in the cells. That's our case. So we can either use RNA interference, and that would give us a transient short-living model. We can use hairpin RNA, and if we introduce them using a virus, a retrovirus, that would be quite a permanent model with a constant gene knockdown. We can also use genome editing by TALEN or CRISPR, and that would give us a permanent model with edited genome, just lacking the gene of interest. For most cancers, the model creation is from the opposite, to activate mutations. That would be, for example, for melanoma, that in most cases has active RAS. So we would activate RAS by either site-directed mutagenesis or by overexpressing the protein of interest in the model cell. Or we can just go directly to exposure to mutagens. For example, the prostate cancer model includes just given mechanical alterations, permanent mechanical alterations to a rat prostate. Or we can also use the CRISPR for introducing activating mutations. And there is one more way to obtain a cell-based model. It's an extraction of the cells from patient samples. So to get the NF2 model, we excluded the NF2 gene from mouse embryonic fibroblasts. So in embryonic development, Merlin is expressed nearly in all tissues. And we chose quite rapidly dividing mouse embryo fibroblasts to introduce the Cre recombinase sites in NF2 gene exon 2. And then we just used Cre recombinase to exclude the gene, the exon 2 piece of NF2 gene. Why would we use such a model is because we still had the original cell line, the mouse embryonic fibroblasts, with this flox allele, the Cre recombinase site, as a control line. And this pair was only different by one single gene, the NF2 gene. So all the studies that we were performing on this model were all the findings in the studies that were performed on this model were definitely defined by the absence of this single NF2 gene. So you can see that we lost the Merlin expression in our model cells, NF2 minus cells, and that's also the PCR confirmation that the gene was excluded. So when you create a model, you need to make sure that your model is working. So what we have here is the difference in the morphology of the cells. You can see that NF2 deficient cells are adhesive. They definitely have some disruptions in their actin skeleton. They do not look as alert and tense as NF2 normal cells, but they are growing much faster than the control cell line. They are resistant to medium starvation, and they are also resistant to certain poisons. And this one is a pan-kinase inhibitor, staurosporin. These cells are generally more aggressive and resistant to alterating impacts. Thus, we confirmed that our model is working and moved to the next stage, which was actually the bioactive compound screening to find the potential NF2 therapy. We had at hand a bioactive compound library consisting of almost 500 drugs and known bioactives, not only drugs, but also poisons and naturally occurring active compounds. And we did a non-selective high throughput screening. So we were not looking for a certain group of targets. We were just screening all the drugs that we have at hand. The screen also included the synthetic lethality by introducing this inactivating mutation in NF2 gene of the model cells. And we were looking for the ratio in survival of NF2 to control cells to be below 0.8, and also the false discovery rate to be below 20%. That's the impression of the bioactive compound library, which included drugs, adrenomimetics, adrenoblockers, cholinergic and anticholinesterase agents, serotonin and dopamine modulators, non-steroid anti-inflammatory drugs, steroid anti-inflammatory drugs, prostaglandins and arachidonic acid derivatives, potassium channel blockers, calcium channel blockers, sodium channel blockers, estrogens and anti-estrogens, antibiotics, cytostatics, immune modulators, apoptosis inductors, lipid synthesis inhibitors, and many other groups. All the compounds were present in DMSO as DMSO solutions at 5 mg per ml. So, the standard screening includes several stages. The first one is the screening itself that revealed 9 compounds qualifying to our screening criteria. And the most important stages are the screening result validation. So the first stage includes the IC50s and the dose effect curves. And we found out that only 4 drugs presented normal sigmoid dose curve effects, dose curves. With stable and consistent difference between viability of NF2 deficient and control cells. We next tested the compounds on NF2 deficient tumor cells, on mouse schwannoma and rat schwannoma, to make sure that these drugs also work on naturally occurring NF2 associated tumors. And these left us with 3 drugs. Then we re-expressed Merlin in the model cells and found out that only lovastatin and Cyrilline lost their effect. This one, the third drug, resveratrol, still continued to work on cells with Merlin re-expression, which indicates that it might not be associated with the absence of Merlin. And finally, we also tested the other drugs from the pharmacological group and found out that both lovastatin and Cyrilline were typical representatives of their pharmacological groups. Now I'm going to discuss the stages in details. So these are our 9 compounds. You can see that lovastatin was the most effective, and the second was Cyrilline. And all the other drugs were actually approaching the criteria of viability ratio below 0.8. Here are the dose curves, and you can see that all the 4 drugs expressed express a nice selectivity against NF2 deficient cells. And all the three drugs, lovastatin, Cyrilline, and resveratrol, work on naturally occurring schwannomas. SC4 is the mouse schwannoma, and RT4 is the rat schwannoma. So they all express nearly the same IC50, the half inhibitory concentration in all these NF2 deficient cell lines. And when we re-express Merlin in naturally occurring mouse schwannoma, we get the loss of vulnerability, of sensitivity to the drugs. This indicates that Merlin is definitely involved in the mechanism of action of these drugs. And pharmacological analogs also quite nice selectivity against NF2 deficient cells. So now we're going to discuss the second part of genetic technologies in pharmacology. And I'm going to give the two examples of investigating the mechanism of action of a found drug. So we found out that lovastatin and Cyrilline were both selectively killing only NF2 deficient cells. But we still do not know why it is happening. And the ways of investigating the mechanism of action can be different. It, of course, depends on the target that the drug is aiming. But I hope that these two examples will give an understanding on how the first look should be taken on what to focus on and how to plan the studies to be able to find out why the drug is working. So I'm going to start with Cyrilline, which is the fatty acid synthase inhibitor, and its analog C75 that was found in the pharmacological analog studies. So they both inhibit the fatty acid synthase. And the first thing to actually check was to knock out the fatty acid synthase itself and to see if the genetic inactivation of the enzyme would cause the same effect. We used the hairpin, short hairpin RNA targeted against fatty acid synthase gene, and saw that it also selectively caused apoptosis in NF2 deficient cells. Here you see the anti-fatty acid synthase shRNA, the decrease in expression level, and increase in the apoptosis marker, the caspase-3. And the same effect was observed with Cyrilline, also a huge increase in caspase-3. And also, for some reasons, it genetically modified the expression of fatty acid synthase. So it was probably also working on the transcription factors for fatty acid synthase. And you can see that there was no such effect on control cells, same as the non-silencing RNA in the control cells. So we found out that fatty acid synthase indeed was the reason of selective action of Cyrilline. And now we need to look on how fatty acid synthase works. So it's a huge enzyme that produces palmitate from malonate. And all the stages of this synthesis from 4 carbons to 16 carbons is made by a single enzyme. And this enzyme is fueled by acetyl-CoA carboxylase that produces malonyl-CoA from acetyl-CoA. So what would be the ways to modify the activity of fatty acid synthase and acetyl-CoA carboxylase? We can either block, that's what shown before we actually started our studies. It is known that Cyrilline is blocking the condensation of melanyl CoA to produce butyryl CoA, and melanate starts accumulating in the cell. So there might be two reasons for Cyrilline to work on NF2 deficient cells. This could be either the deficit of palmitate when fatty acid synthase is blocked, or accumulation of the melanyl CoA, which can be toxic at high concentrations. To find out which one is the correct hypothesis, we try to supplement the growth media with palmitate and see if it eliminates the effect of Cyrilline, and it did not. So not the deficiency of palmitate was the reason for the NF2 deficient cell death. Then we deemed that the accumulation of melanate might be the reason, and to check that, we need to modify the amount of the fuel entering the fatty acid synthesis. This can be done by modifying the activity of acetyl-CoA carboxylase. We can either activate it by 5-iodotubircidine, or we can block it by tetroxyfuroic acid. Or we can again use the genetic technology and just knock out the gene for acetyl-CoA carboxylase that is called EKK. And indeed, when knocking out this EKK gene, we got the decrease of sensitivity to Cyrilline in NF2 deficient cells and even in NF2 flux cells. The chemical modulation of acetyl-CoA carboxylase activity also gave the same effect. When inhibiting with tetroxyfuroic acid, we get the loss of sensitivity and not so much in the NF2 flux cells. There is a reason for that. I'll explain later. And when reactivating with 5-iodotubircidine, we get the increase in sensitivity, and this increase is much more prominent in NF2 control cells. Again, I'll explain why it's happening. So the hypothesis would be that the accumulation of melanate is the reason for the cell death, and the difference in the cell death rate would be that NF2 deficient cells metabolize more quickly. And that's why they die at lower concentrations of Cyrilline. To check that, we need to evaluate the metabolism rate in NF2 deficient and control cells. So there is a huge amount of additional enzymes involved in fatty acid synthesis. They do not synthesize fatty acids themselves, but they provide fuel, they are carriers, they are transporters, and so on. So we tried to evaluate the expression levels of all these lipogenic enzymes. And found out that most enzymes express at much lower level in control cells, and the loss of NF2 gene causes the increase in expression indeed. Also, for activity of the proteins, for the phosphorylation levels, we found out that phosphorylation level for active proteins is also higher in NF2 deficient cells. And for acetyl-CoA carboxylase, that is inactivated by phosphorylation. On the opposite, I'm not showing it here, but on the opposite, the phosphorylation level was much lower in NF2 deficient cells. And that is why 5-iodotubirsidine did not work on them. And on the opposite, when we re-express Merlin in mouse schwannoma cells, we get this loss of expression level for most genes, for most proteins. And the same is observed when evaluating the matrix RNA level by RT-PCR. So there is a huge difference between NF2 deficient and control fibroblasts for most genes, especially in the beta oxidation group. And when re-expressing Merlin, we get this decrease in expression levels. So the final proof that metabolism level is much higher in NF2 deficient cells was to measure directly the metabolites in both cell types. So you can see that for acetyl-CoA, the level of acetyl-CoA and in NF2 deficient and in control cells is nearly the same, maybe slightly higher in NF2 deficient cells. But when adding Cyrilline, we get the opposite effects. So the fatty acid synthase is blocked in NF2 control cells, and they stop producing acetyl-CoA. But on the opposite, when Cyrilline blocks fatty acid synthase in NF2 deficient cells, we get an increase in acetyl-CoA because these cells are trying to produce more energy and produce more lipids, and they do not stop metabolizing and get this accumulation of acetyl-CoA that has no way out to be utilized by fatty acid synthase. And this situation is even more obvious when evaluating malonyl-CoA. So normally, the level is nearly the same for NF2 deficient cells and control cells because the fatty acid synthesis level is so high in these cells that they just utilize all the melanate in normal conditions. And when we add Cyrilline, again, the control cells, the healthy cells, just stop metabolizing and try to wait until the Cyrilline is washed away. And NF2 deficient cells, on the opposite, as their metabolism is much higher, they cannot just stop and they start accumulating malonate. And that actually starts apoptosis of a certain chain of pro-apoptotic gene activation by malonate. Oh. So we found out that Cyrilline selectivity against NF2 deficient cells was due to their faster metabolism rate. But we also had the second drug that gave very good results in the screening. And this one is a completely different drug substance. Lovastatin is a 3-hydroxy-3-methyl-glycerol-CoA reductase. And this enzyme does the cholesterol synthesis. So again, we first checked if the genetic knockdown of this enzyme, HMG-CoA reductase, caused the same selective toxicity effect, and it did. I'm not showing it here because it's too long. But now we again try to understand why the cholesterol synthesis disruption causes this selective toxicity. As I've said before, statins suppress the HMG-CoA reductase that produces mevalonate, do not mix up with melanate, from acetyl-CoA. And the final step is cholesterol. But the synthesis chain also has a certain amount of intermediate products. So again, we tried to supplement the media with cholesterol, and it did not reverse the statin's effect. We still had the same selective toxicity. But unlike the fatty acid synthase, there is no accumulation of intermediate products because this is the very first step of the synthesis. And only acetyl-CoA can be accumulated, and it's not toxic at all. So we thought that some of the products could be, the deficiency of some of the products might be the reason. And we tried them all. We tried the squalene ring, we tried mevalonate. Squalene ring did nothing, lanasterol did nothing, but mevalonate had the same supplement completely reversed the toxicity of statins. And so did isopentenyl phosphate, geranyl phosphate, and farnesyl phosphate. And even this guy, the geranyl phosphate, which is the side chain, but still it is definitely produced by HMG-CoA reductase from acetyl-CoA. So what do all these guys do? We've gotten the farnesyl phosphate and geranyl phosphate that are the last steps that reverse the statin's toxicity. They are both short chain lipids, the phospholipids. So they have a polar end and non-polar end, and they are used to modify certain proteins. For example, farnesyl phosphate is used for farnesylation of RAS protein and some other proteins. And geranyl is used to granulate raw RAC and other proteins. Granulation and farnesylation allows these proteins to anchor at the cell membrane. So for RAS, this will cause proliferation because RAS can be anchored at the membrane and perform its functions, and they are in regulation of proliferation. And for Rho and RAC, this means also anchoring at the membrane and performing their functions that are motility and migration regulation. So might it be that the deficiency of functions of RAS or RAC caused the selective toxicity effect? We tried supplementing the growth media with farnesylase inhibitor that is called farnesyl thiosulfate, and it did nothing. It was toxic for both NF2 deficient and control cells. But when we did the inhibitors of geranyl transferases, the PAN transferase inhibitor zoledronic acid, and also selective geranyl transferase type 1 inhibitor, we caused the same selectivity that the statins did. And this means that some of these geranyl transferase enzymes, and most likely the geranyl transferase type 1 enzyme, is causing the selective toxicity of the statins. And this means that we should look into the granulated proteins that are actually granulated by this GGTI enzyme. So we looked into the protein sequences at UniProt that had KX motif on the C-terminal. What is KX? That's cysteine to aliphatic amino acids and any amino acid. And that's these 4 amino acids signal to the geranyl transferase type 1 protein that this target needs to be granulated. And we found that around 79 proteins in the human proteome and around 160 proteins in the mouse proteome could be potentially granulated by GGTI enzyme. And the most important groups of the proteins included Rho GTPases, RAG GTPases, RAL, and RAP GTPases, and also certain G protein subunits. we might create a small interfering RNA library to just knock down all the proteins that we found that had this KX motif and see how many targets we would get. Supposedly that knocking down such an enzyme would cause either the loss of sensitivity to statins or just the selective NF2 deficient cell death. But we decided to first start with the key groups of the granulated proteins and see if we could find any peculiar things. And we were lucky enough to find those. So we suppose that the deficit of function of this granulated protein would be the reason. But on the opposite, we found out that activation of RAC1 protein caused the cell death in the presence of statins. So what we did was we generated this constitutively active form of RAC1. And when modifying the cells with this mutant form, we got an increase of sensitivity to simvastatin, even in the normal cells. So these cells do have an F2 gene, but they have an active RAC1 form, and they just start dying from simvastatin. They were not sensitive at all, and then they obtained sensitivity. And on the opposite, when we use the transit knockdown with anti-RAC1 siRNA, we get the loss of sensitivity. So just knock down the RAC1 from NF2 deficient cells and they lose their sensitivity to statins. And we need to remember that RAC1 is inhibited by Merlin. So in NF2 deficient cells, RAC1 is actually active. And that might be the reason why they are sensitive to statins. So we found out that the gain of activity of RAC1 in NF2 deficient cells and probably disanchoring RAC1 from the cell membrane caused cell death. So the next step was to see what RAC1 was doing in the cell. And to trace that, we labeled RAC1 with green fluorescent protein and just did the fluorescent microscopy experiments when transforming cells with this fused RAC1 GFP protein and adding lovastatin or simvastatin. And we found out that within an hour, almost all the RAC1 protein was localized in the nuclei of the cells. In the NF2 deficient cells, in mouse schwannoma, and in the module fibroblasts. But there was no such effect in control cells. But nonetheless, in 24 hours, all the cell types had their RACs localized in the nuclei. So obviously, the difference between NF2 deficient and control cells was in the one. And to check that, we used the Forster resonance energy transfer method to measure RAC1 activity in the nuclei and in the cytoplasm. So we had, again, the genetically modified RAC1 protein that was tagged with cyan fluorescent protein, CFP. And we also had the RAC1 substrate PBD. Do I have a picture here? No, I do not, unfortunately. But the RAC1 substrate PAC binding domain is such a small piece of protein that is always interacting with active RAC. So when you have an active RAC, it will definitely interact with PBD. And if you label PBD with yellow fluorescent protein and have the RAC1 tagged with cyan fluorescent protein, you get the loss in cyan signal and an increase in yellow signal. That's the Foster resonance energy transfer, actually. So we found out that, as you can see, when adding lovastatin, we get all the RACs in the nuclei in both cell types, in NF2 deficient cells and in control cells. But in the control cells, in the presence of lovastatin, RAC1 is not active in the nuclei. You can see it by the blue color, which is absolutely cold protein, not active. But in the NF2 deficient cells, you can see that the nuclei have the bright orange color that indicates the high activity of RAC1 in the nuclei. And that's the numerical presentation. So indeed, the selectivity of statins and zoledronic acid against NF2 deficient cells was because of the activity of RAC1 in the NF2 deficient cells, and because these drugs removed RAC1 from the membrane, causing its translocation to the nucleus. So now we are working on the further clarification of the mechanisms by which active RAC1 kills the cells in the nuclei. But it's now obvious that this can be transferred to any oncology that is dependent on active RAC1. So it probably can be applied to breast cancer and some certain forms of skin cancers that have active RAC1 in pathogenesis. So the last step for such pilot non-clinical studies before the found drug would go to the further efficiency and safety evaluation program would be to test it in the living organisms. So here you can use either a genetic model of the disease by using a transgenic animal, or just do the xenograft studies. So for us, there are NF2 deficient transgenic mice, but unfortunately, it's not a good model because in humans, NF2 develops by 8 years of age. In mice, the first tumors only occur at 6 months. So when the animal is an adult animal, actually middle age, and neurofibromatosis type 2 is much lighter for mice than for humans. So it's not a very good model, but you can just get the samples of the tumors or grow up some model cells like rat schwannoma in our case, or mouse schwannoma, and just implant it subcutaneously or into the nervous system or whatever model you use, depending on how good your animal surgeon is at the animal facility, and get the graft tumors and test the efficiency of the drug in the whole living organism, but in the model tumors. And you can see that all the tested drugs did slow down the tumor progression, but unfortunately they did not cause the tumor shrinkage. So this is an indication that we still need to work on the drugs. They probably cannot be used as a single drug, but we can probably find a combination drugs for them. And when we get this tumor volume shrinkage, we can probably move into the second stage and do the more thorough, full non-clinical studies to be able to market the first ever NF2 treatment. And to summarize our findings and to summarize the application of genetic technologies in the novel drug development, I just want to say that we found the first target for NF2, which is fatty acid synthesis, and also that can be modified by Cyrilline and other inhibitors. And also we found that when removing RAC1, the active RAC1 from the cell membrane, we can also cause the cell death induction. So at least 2 novel targets discovered, and that's the way for future investigations. Genetics rules.